Uh, so, so, so far, what we did is that on week one, we talked about um, um, basically four types of database, and we are only focusing on the relational database. However, from practical point of view, some of the other databases like uh, whatever, like NoSQL is one of the popular thing, which is the hierarchical kind of database in which those databases are not relational. That is also important area to explore. Second lecture, we talked about the ERD, and that ERD is called design by analysis. Design by analysis. For example, when a database developer get a paper of description about the system to develop, then the way we got a description in the exercises, and then we try to make the ERD, entity relationship diagram, and EER out of it, right? So that is called the top-down design, and that we covered last week, and we went all the 9 steps. Uh, if we want to cover the EER as well. Now, this lecture is to look at the database design from a different perspective. That's called bottom-up approach, but mainly this is design by synthesis. For example, I went to my friend's office, for example, and he want to develop a database with me, and he can show me the front end, for example, like all the forms, for example, right? The contact form or any application interface in which, the client information needs to be inserted, total sales are shown. So based on those forms or web interface or application interface, we try to come up with a database design, right? That is actually today's lecture, is the normalization, right? So it's really developing the database from a different perspective. That's why this is really, really important. One way to check the whole two process is to kind of cross check to see what's really happening and which one is optimal. And ultimately the decision is with us, how to which one is the optimal and so on. There are other factors as well. So even the SQL, when you go through the SQL, the join, to actually talk about relational algebra, some of the ideas will also come to select the optimal ones. Okay, so this is the difference, that normalization is the bottom-up design or design by synthesis, and ERD is the top-down design or design by analysis. Okay, another question I think came in the forum regarding the software to draw the ERD. You can use any software, including MS Word, Visio, Draw.io, or whatever you like. Now, what is normalization? So normalization of user view. So this term is really important, the user view. And so what are the steps the steps are to represent all user views, like the forms, reports, as a collection of relations. So one form will try to reveal a relation, definitely. And another form will reveal another relation, right? A report, it can be written report, it can be printed report, or the form they're using in the office. So when we'll go through the exercises, then we'll get more ideas about that. So from all those reports, we can get a collection of collection of relations. Normalize these relations. So the next step is those relations. We need to normalize that. Why do you need normalization? The main problem that will happen at the beginning is that the same problem that we covered week 1, which is the data anomalies. There are 3 types of data anomalies. I think one of the question in the first lab, like the insertion anomaly, deletion anomaly, and modification or update anomaly. So if we have a big table, then we know that if we insert a new data, we need to insert associated attributes. And sometimes it increases the repetition, right? And similarly, we'll see more examples in the coming slides, but these 3 types of problem will happen at the beginning. Now, to minimize those anomalies, we need to normalize the relations. So one way to normalize the relations is to break down the tables. So a big table, we need to make it partition. So that we will see. And combine relations that have exactly the same primary keys. Combine relations that have exactly the same primary keys. So we'll see in due time. Now, the first thing in normalization, the first concept in normalization that we need to understand is called functional dependencies. Functional dependencies, and these dependencies are based on the dependency between the attributes, right? So that we'll try to first understand. So a relational table is one way of describing the way in which several attributes interact or depend on each other. So the simplest kind of dependency is called functional dependency or FD. So something on the left-hand side tends to right-hand side. So right-hand side depends on left-hand side. So we'll see an example. For example, lecturer ID tends to lecturer name. So that means that if I know the lecturer ID, I can tell that what is the name of that lecturer, right? And also we can say other associated attributes as well, right? Everything we can say just based on the lecturer ID. So of course, I mean, it is closely linked to the primary key. So I haven't yet revealed the word primary key. So I'm just trying to start the discussion going, I mean, initiate the discussion from the very scratch, from the very beginning levels, that this dependency we need to first know that this one is depending on that. But the other way around, I mean, that's not really possible because, there can be duplicate same name. So this one is a valid FD or function dependency because for each lecturer ID, there is at most one lecturer name, or lecturer name is determined by the lecturer ID, or lecturer name is uniquely determined by the lecturer ID, or lecture name depends on lecturer ID. So the last sentence is really most of the time it's said. So each of the above statements is equivalent, right? So this is one concept. Now, one of the thing is that there can be multiple attributes on the left-hand side. There can be multiple attributes in the left-hand side. Yes, Sandeep, do you want to ask anything? You can.
Can you hear me now?
Yes, yeah, that's
Beautiful.
fine. Yeah.
Just wanted to confirm, it has to be the primary key, isn't it?
No,
You
I haven't said primary key yet, right?
okay? So can you determine the lecture ID from the lecture name? Lecturer name.
No, that I said because I mean, two lecturer name can be same, right? I mean, more than one. So
Yeah.
really, we can't say that, right? For
Okay.
example, if there are two lecturers like Manzoor,
Yep.
then it's confusion, right?
Mm, okay.
That's why you can't
It has
say
to be unique.
correct, correct. So ultimately, we are going there in the primary key level, right?
Sure.
So yeah, so this is one of the thing. Okay. Now some another definition, another really important definition, which is the full dependency and partial dependency. Okay, so full dependency is if I say X tends to Y, then it is called a full dependency situation if no attribute can be removed from X. So it looks like only one attribute, but it can be a collection of attributes. It can be more than one attributes. So in that case, we can't really isolate them. Okay. So what's the example of that? For example, if I say lab date and subject code in university, both together defines a tutor, right? Uh, so if we try to isolate one, we can't really define a tutor, right? Because a subject code can have multiple tutor, right? And a particular specific date can reveal that which tutor is tutoring now, right? So it depends on both. We can't really isolate them, right? So one of the side note I would like to say is that assumption is one of the most important thing here in some cases, right? In some cases it becomes really important because sometimes argument can happen, but if we can assume that this is a situation, right, that we'll see in one example basically, then our arguments would be strong, so this is the logic. Anyway, coming back to here, that's why we can say that this is a full dependency situation. So tutor is fully dependent on both. Another definition is called, a different definition is a partial dependency. So if x tends to y, and if any attribute can be removed from x, then this is called partial dependency. So for example, if we say lecturer ID and subject code tends to lecturer name, this is partial. That is, the lecturer name is partially dependent on the lecturer ID and subject code, right? That is, the lecturer name is partially dependent on lecturer ID. So, which means that in fact, lecturer ID is really dependent on the lecturer. Sorry, lecturer name is really dependent on the lecturer ID. But if we think both together, that also reveals the same thing, right? No one can deny that because we can think in this way: a subset, if defines something, then the whole set, of course, defines the same thing, right? I mean, it must be true. So this is what it is talking about in this particular case. Or if we think a table, we can say that like my ID and I'm teaching a subject, that depends who am I, right? At the same time, only lecturer ID can also defines who am I. So if we can find a situation like that, we can say that this is a partially dependent situation. These situations are really important because based on those situations, we need to make smaller tables or do something that we'll see in the normalization. So these are the two very important definition. And the third definition, then actually we can start the normalization steps, is called transitive dependency. So dependencies can be transitive. For example, if one lecturer can teach one subject and each subject has only one tutor, then we might have the dependencies like that. That lecturer ID tends to subject code that is revealed here if one lecturer can teach one subject. And each subject code has exactly one tutor. So we can say that lecturer ID, it's simply by logic, right? It's a logical kind of reasoning. We know that if A tends to B, B tends to C, then A tends to C, right? So similarly, lecturer ID can, so tutor basically depends on lecturer ID. So this dependency we can define based on these transitivity, right? So this relation is called transitive relation. Okay, so there are three definitions we found. One is that full dependency, in which we can't really separate any attribute from the independent part, I can say. Here we can isolate any attribute. That's called partial dependent, and there is the full dependent situation. And in fact, for full dependency situation, we can't do anything, any kind of separation of the tables, or we can't make in most cases, not every time. But in partial dependency, there we can do something, right? We can see here that we can really isolate here the subject code, and we can do something else that we'll see. And in transitive dependency, let's see, we'll see what we can do. Probably in a different situation, it can appear in the table, right? So these are the three definitions. Now, look at an example. So functional dependencies can be used to decide whether a schema is well designed or not, right? So these functional dependencies can really be used to decide that. And based on that, if it is not well designed, we can do something else. Now, look at an example, a big table like lecturer subject, lecturer ID, lecturer name, subject code, subject name, and term, right? Everything is here. So if we can just try to think this particular table, it is probably similar to the big table of first lab, right? And we there actually we can imagine that there are some anomalies we can easily see here. What are the anomalies? There are three types of anomalies, like the insert anomaly. For example, if I want to insert a new subject, then we must have to assign a lecturer. Otherwise, we can't really do anything in this table, right? So if we want to insert a new subject, a lecture ID must be inserted. That's called insert anomaly. Update anomaly. So if I need to change an existing subject name, right, then in every instances where this exact thing is appearing, we need to update it, right? That's really problematic thing, right? And the deletion anomaly or delete anomaly is if a lecturer, for example, a lecturer is teaching three subjects, a lecturer is teaching three subjects, and probably two of the subjects are taught by other lecturers. However, he is teaching one specific subject that is only taught by him. So if that lecturer resigns, right, then that row will be deleted. And if we delete that row, then only, probably all the three subjects would be deleted. But since other lecturers are doing the two, those subjects instances would be there. However, one of the subject that is exclusively be taught by this lecturer will be deleted forever, right? So in other words, some subjects will be removed permanently from the database if that lecturer is teaching that subjects alone, right? So that's called delete anomaly. So that problem we can easily see from here. Now, design errors in relations such as potential for certain kinds of anomalies can be categorized, right? We already categorized in three ways. These categories of error can be successively eliminated by decomposing relations into normal forms. Now, how to do that kind of normal forms? The first step is first normal form, then the second, then the third BCNF at the same time sometimes, then fourth and fifth. So now there are two reasons that what we'll be doing, we limit ourselves on until 3NF or BCNF, so up to that point. So there are two reasons. One is that the research studies have shown that most, in most of the cases, up to BCNF, if we can do like the third normal form, if we can normalize, then the anomalies are no more, right? We can successfully eliminate that. And also these up to three, up to BCNF, all these four basically uh, can be identified. All the, the normalizations can be solved, or the approach can be progressed using the functional dependency principles. We already talked about three principles, right? Partial, full, and transitive. So with functional dependency, actually things can be identified easily. But the higher normal form, and already another point is that already with third NF, you have lot of tables. You have lot of tables. Now, uh, further normalization means that you need to make more tables out of it, right? More tables out of it. That's the main objective, right? So that the main objective is to reduce the anomalies and other things. So 4NF and 5NF are basically depending on the join, not depending on the function dependencies. It's going to join dependency like other tables. That is, it is hardly used in even in theory basically. Plus the problem, the downside is that this 4NF, 5NF will create many tables. Now the practical implication of many tables is that the danger of joint relationship. Very soon in SQL, we'll know that even in relational algebra, that multiple tables can be joined together. So when we join multiple tables, then it it is doing Cartesian product that we discussed last lecture. That, for example, one table has four tuples, another table has four tuples. So in join, initially, like in the Cartesian product, it creates 4 times 4, 16. So imagine if it is a 1 million entry, 2 million entries, right? So huge number, a huge table will be created. And from that table, you need to search based on same ID that will exclusively going through. We'll discuss when we'll discuss about the relational algebra. Then we try to pick only the common portion, right? So what I'm trying to say is that in 4NF, when you make more tables, then the join operation you must have to do while doing the queries, and then it will be very expensive operations, right? It will be really very expensive operation if there are many tables. So the research studies show that, I mean, we shouldn't go beyond that. That's why we will stop up to the 3NF. Now, these forms are increasingly strict, that is increasingly error-free. Advanced normal forms are based on complex kinds of dependency, like I said about join and other things are there. Because problems with 4NF and 5NF rarely occur, right? Moreover, database designers in industry normally do not need to use the highest possible NF for practical reasons. In this subject, we'll focus satisfying 3NF and BCNF. Any question from anyone up to that point? Or any comment? Okay, excellent. So we proceed with that. Now, these are the simple steps. So first is we get a table that is given like a form or anything that's called unnormalized form. So whatever attribute we can pick, we just put it there. And that is called basically unnormalized form. That is a way to put it there. However, I mean, whatever attribute anyone can find from a form, from a discussion or whatever, this is unnormalized. So we haven't yet started that. So first normal form is that when you get an unnormalized form entity, unnormalized form tuples in an entity, then the first normal form is a relation. Relation means that particular entity. If there are no repeating groups, so if we don't find any repeating groups there. Second, a unique key has been identified for each relation. So this is the first time the PK or primary key concept is coming up here, right? All attributes are functionally dependent on all or part of that key, right? So that kind of notation we try to pick. Now, one of the things is that even the PK unique key is mentioned now, not primary key, because probably when we do the normalization, then that's the if there are three selected in any normal form, that can be two, that can be one, which means all were unique. But ultimately we come to the point which is the kind of very efficient or optimal, kind of unique key, and then finally we can define it as a primary key. That is the final in the final output, right? So, but in each step, we define it as a unique key. We can also say candidate key, right? So later, basically, it will finally will define it as a primary key. And all attributes are functionally dependent on all or part of the key. So look at that, all both options can be valid at this stage. A second normal form is a relation. It is in 2NF. I can define that, okay, this is a table, this is a relation. It is in 2NF if it is satisfying first normal form and some additional kind of constraint, additional kind of, qualities, which is that the relation is in first normal form and all non-key attributes are fully functionally dependent on the entire key. So we need to check that is there any partial dependency there or not. So if you can recall from first normal form, that there is statement that all attributes are functional dependent on all or part. So if it is on all, then you don't need to do anything basically, right? Then it is already in second normal form. But if it is part, then we need to do something to remove that partial dependency, and that is why it is called that a second normal form is a relation which is first normal form and the partial dependency has been removed. Okay, which means a partial dependency can only happen when if it is a composite primary key, right? If there are more than one attributes is defined as a unique key or primary key, then only we can think for second normal form decomposition. Decomposing the relation to make it second normal form. Okay. Uh, so any question up to that point, you can then talk. Otherwise, I can proceed. Now, a relation is in third normal form. So if it is second normal form, which means that, step by step. So we have to finish the second normal form, and then we have to find any transitive dependencies. So if there is any transitive dependencies, so transitive dependencies of what? So this is really interesting statement that a non-key attribute depend on another non-key attribute. So suppose there are 5 attributes. So 2 of them are, or 1 of them is primary key. So non-key are remaining 3 or 4. So if we can find a functional dependency between those non-keys, that means that dependency even can happen on any keys, really, right? Then that is called transitive dependencies, right? And that we need to fix. We need to make another table to fix it. And when we'll go through that table, then the concept would be really, really simple, right? It's really simple. Okay, now that is actually happening. Now, a specific form of hard normal form, a kind of variant, which is the Boy's code normal form, BCNF in short, that the relation is already in 3NF. However, any remaining anomalies that result from functional dependencies has been removed. So even after that, something can happen. Something can happen. Some unusual thing can happen that I'll really discuss. So I can say that. I mean, in this particular case, for example, if I say that if A is a primary key and B tends to C, right? And sorry, I just need to probably do one thing here. Um, okay, so if I say that, say A, right, B is a primary key tends to C, but somehow I found that uh, B is depending on C, right? So it's a really kind of an exceptional situation. It can also happen something like that, that one of the key is really depending on another non-key. Then it's an unusual situation that never happened up to the 3NF. So then we need to do something else here, right? So this type of situation is called basically the BCNF. We'll see in due course, basically that thing. Okay, sorry. Okay, so I think up to that point, we just defined all the steps. Now, when we jump to an example, it would be really clear. Now, we see an example, and then we'll try to discuss that how we can make a database or relations out of this form. Now, I said at the beginning that this is a design by synthesis. So suppose we can see a front end. Record. So we can see a front end in which they're asking to me to develop a backend database out of this form, for example, right? So by looking at the form, we can um, try to define the attributes, right? So we can imagine that this is definitely the column header, right? Of the attributes, and these are the values. And so we see that for a particular order number, there is a customer number, the details of the customer, order date, and we can see multiple products, right? So these multiple products, we can say that it is a repeating groups or repetitive groups, right? So it is repeating, but this name and order number is fixed, only one. So from in one of that order, we can see not everything repeating. These portions are one, but the products sections, like these four attributes, are repeating, right? So we can say that, I mean, that currently this is in unnormalized form. So what we should be doing here is that I can do one thing, just, okay. So sorry, just try to explain in a simple way. Sorry. Hey, I would like to keep side by side. To explain the thing. Okay, and now, share this screen. Okay, so if we look at these particular example on the left side, that for a particular order number, we can see the repeating group. So what we should be doing is that first we'll write it down. Everything we'll write it down. So order, it's an order. We start a bracket, first bracket, and then order number, customer name, address, everything we write down, postcode, order date, comma, and then this is the repeating group. So we should never write everything, right? It's just endless kind of thing. So we just put the attribute using an extra pair of brackets, right? So we put another bracket, extra bracket, and then we write these four attributes: product number, description, quantity, and unit price, and close this bracket, close. So when we put a repeating group, we need to define a repeating group in this particular way. We put an extra pair of brackets, right? By this way, we know that this is a repeating group. So this, if we look at the definition of first normal form, we know that there are no repeating groups, which means that we have to do something. Otherwise, we can't really start even the first normal form. That is the start of the normalization. And once we remove the repeating groups, then we can think of a unique key, right? According to these steps. Now, what we can see here that to convert the above relation into first normal form, the repeating group must be removed by creating a new relation based on the repeating group. Look at that, along with the primary key of the main relation. So what is the primary key of the main relation? Who can tell me? Which attribute do you think is the prime? Sorry, anyone?
Order number.
Order number, excellent. So that order number, so to say that we have to create another table, so definitely this primary key should also go there, right? That is actually mentioned here. So if we look at these, that idea, that the order, we see the order number, customer name, order date, we stop up to that, and then we put another relation that is the desired thing, and we put this for product number, description, everything, and we put that order number as a foreign key. Now, one notation is that for the foreign key, it would be italics, right? In italic form. So this one came, and since this is the primary key also here, so this is a joint primary key, right? It makes sense that because this order product table, definitely, it should be the I mean, partial key as well. So they are combined or composite primary key, right? So any question up to this combined primary key, or any basic question from anyone? Okay, all good, right? So this is how, in fact, if we don't put the foreign key, we can't really relate them, right? That is one of the interesting things, that the way we have to relate them. That's why it is really needed. Now, when we come up with come to the point of first normal form, we need to check immediately the anomalies. What data anomalies can happen? So if we look at the insertion anomaly, so we can see that uh, the same thing is the same problem is still there, that we cannot insert a new product until there is an order, right? So we can't really, in this database, suppose it's a complete database, we can't really insert a product until the order name is issued, right? Or deletion, if an order is deleted, the product can be deleted if that product, suppose, is not anywhere. So that product will be deleted forever. Update, again, the same thing, that if we change any description, then for every instance we need to update. Otherwise, what will happen? Suppose this product is appearing 5 times, we updated 3 times, then this problem is called inconsistency, right? Inconsistent data, and that is actually one of the big trouble in the database, mainly in the data analysis, right? That and sometimes it's really can't be solved. That's why we are really concerned about removing the anomalies as much as possible. Okay, so we can see that these 3 anomalies are still happening here. Now, second normal form. So the order product relation. So if we see here, so what is second normal form? So if we recall, the definition of the second normal form is that it must be first normal form plus, if there is a partial dependency, like, I mean, just try to imagine that the partial dependency can only happen if there are more than one primary key, right? If it is a composite key. So if there is only one primary key, then don't bother about second normal form. You don't need to think anything, right? Probably in third normal form, we can do some investigation to that relation. Otherwise, we don't need to. Now, in second normal form, we have to check the partial dependency. So here we can see that the order product. So now we have to compare from here, basically from the first normal form. So in the first normal form, the order, we don't need to, we're not bothered because only one primary key. So only things can happen here, right? Things can happen here. So in the order product, Not all non-key attributes are fully dependent. So what's really happening here that uh, we can see that the product description, quantity, unit price are really depending on the product ID, right? Not the order ID. So we can see that there's a partial dependency. We can easily see from here. I made a mistake. So not the quantity, right? So description and the unit price, they are depending on the product number. So this partial dependency um, gives us an indication that we need to, partition this table. We need to partition this table, and the way we can partition is that, okay, definitely product description, unit price can go to another table where product is the primary key, and the order product table should be order ID, product ID, and quantity, in which um, product ID or product number becomes the primary key, right? Primary key for this table, but it is actually foreign key because this came from the product table, and order. So they together stay as a composite key. So we can see the output like that. That the
Can I just ask
product,
a question, please?
yes, Andrew, yep.
Um, aren't you just creating a relation in doing this? If you had have set your relation up correctly in the first place, that um, you have order, orders, product,
Yep.
as so had an entity and order and a product as an entity, and you had a relation called order, orders, product. Wouldn't
Yep.
this already be solved?
Um, I mean, for this particular scenario, or you
Yeah,
have
for this
to.
particular scenario, yeah, in this specifically in this case, right? You've just got an entity called order,
Mhm.
but you didn't describe the fact that the order orders a product. Otherwise, you'd have an entity called product, and in which case you'd already have the separation of order and product, and you wouldn't get into this anomaly problem.
Yeah, but I think we came to this first normal form based on the form that we see.
Oh, okay, but based on that, wouldn't it be more?
No, because if we have another
Couldn't we go
form,
back to
like
first principles and create the
in a different way, you're saying, right?
well, yeah, in the way that we were taught in the previous lecture, right? We would start with the entities. You've got an order and you've got a product, and then you've got a relation between them, saying order orders product. In which case,
Yeah, I know what you're saying. Yeah, I mean, when we have a kind of a description, then it is really easy to go for, different way to think. We can think that, there's some liberty. But when we have a form, for example, here, this is the order form. Now, probably there's another form in which the product, the um, customer form is there. So customer, how many orders he made, then the order is probably the repeating group, right? And there is another form which is looking at the product point of view. So what we are doing right now, I mean, the basic principle in normalization, in a sense, it is a kind of structure that is really, no need to go or think in another perspective in one particular form, is that for each form, we can have kind of, the relations will be synthesized based on the way the form is designed. And probably another view will reveal another set of relations. Now, out of these two sets of relations, some of them would be common, some of them are disjoint. And by which that we will see actually when you finish this example, then probably what you're thinking, pretty much I'm sure that you're probably thinking another type of form in which basically you're thinking about another way you can define a relation, right? So I think once I finish, then probably you can think about your question, right, Andrew?
yeah, no, it's all right.
Right now, actually,
I,
it's not. Uh,
no,
I
it's
can't
fine.
get
It's just
to a
that
point. No, it's a really
uh,
good point. In a different way, you can think of that liberty was definitely in the ERD, right? But here, let's say, I mean, I'll think then, right? Also. Okay. Now coming back to here. So again, I'm just quickly doing the thing is that this example is just one form. So we don't have that freedom, but the next example we'll see that for a particular situation, we have multiple forms, and that example will reveal its thing that multiple types of relations will be revealed. Now, here, whatever attribute we get, we just simply put everything with the repeating group. And then we try to break it up based on whatever the repeating groups are, and putting the primary key of the main relation here. And of course, I mean, we can think of one to many, many to many, that situation that will be identified. I mean,
Isn't there, I guess, a bit of interpretation that will then kind of determine whether it's, you know, 1NF, 2 or 2NF? Because I could see an instance where somebody looks at this and says, well, let's just make this all a single table. Yeah,
you're saying
obviously
about,
that wouldn't be particularly great.
yeah.
But then this first step, which you're calling 1NF, would
Yep.
then be the 2NF, depending on what you select as the starting point.
No, but the starting point are here really same, right? I mean,
Well, that's
you just put everything,
very,
right?
yeah, but you've got an order form, and we've chosen in this specific first piece to say, well, one table is the top bit, and another table is the second, second table that
Yes.
you had in there. But depending on how this was depicted, I mean, well, I've got purchase
Oh, I
orders and
see.
stuff at work all the time, at work, and the formatting can be
No,
all
but
over the place.
no,
So,
I know, I know. I mean,
so I guess I'm trying to figure out,
mhm.
what's the golden rule to come up with the, quote unquote correct starting point, so that you then don't call something that, yeah. How do you avoid having me calling something 1NF and then the next person calling it 2NF, basically, or say, first order for, yeah.
Oh, I see.
Just,
I mean,
yeah,
no.
how do you pick
Yeah,
that first starting point?
no, the starting point is the unnormalized form, right? That is the starting point. And then the first normal form is just isolate the repeating group. If there is no repeating group, then you just define the primary key, and then it becomes the first normal form. Make sense? Suppose there is no repeating group. So then, is the order unnormalized form. Then only you have to do which one should be the primary key, right? If you put the primary key, it becomes the first normal form. All good
I
now?
think, yeah, look, it kind of makes sense in this example because of how it's laid out. I'm just, I guess, looking back at the invoices
Yeah.
and
So,
orders that I see at work, and
okay.
it
No,
just
that's
wouldn't be
good.
that obvious. And I'm trying to look at it. How do I transpose that
Yeah.
um,
Other situations, right?
into yeah.
That's why, I mean, these examples are well designed. I mean, there are other examples after that. Then, you can get more ideas to think, right? Then
Okay.
see, then I think, you can come up with that question. I think that's the best way.
So,
Yeah.
sorry,
Okay.
Michael.
First, let me finish. So we can just focus on here. Yeah. Sandeep, yeah.
Um, in this unformatted form, the
Hmm.
why
Unnormalized.
a normalized form, why we
Hmm.
haven't gone for like three things, which is like order form, the second is the customer form,
No,
the
just
third is
one
the,
form at a time. I know what you're saying. In the second example, we'll see, yeah, that you just said, three different forms, right?
yeah, I can
So,
see that there are two different primary keys, kind of, and the customer, I would like to keep it separate. Order
hmm.
information I would like to keep separate. So from here, I can straight away goes toward that approach, that I define them separately, like uh,
Okay. Now regarding the different forms, so this is just one this is just normalizing one form. That's it, right? We don't look for other forms right now. Once we finish that up to 3 normal form, then we start with the second type of form that the customer gave us. Then we start from the unnormalized form again. Make sense?
Okay, so
So we just stick to that particular, even sometimes, sticking to that thing that will reveal other ideas. I think this is not that kind of,
I think by the time you get to 3NF, you'll have the separate tables that Sandeep's talking
Yeah.
about.
Yeah, separate tables sometimes,
And this is the process that you go to get there.
Correct. Just it's just
from
a
the
process.
bottom up.
Yeah,
I
excellent.
don't know where the hand up function is. Sorry for jumping in.
Can I just ask also, one of the things that I like about this process is that it takes away the tendency of someone who's in IT to kind of jump ahead and think what the owner of the business might want, whether it be that or not. They've got no knowledge of the business. They come in and they impose their ideas on it, and it might not be correct. So I think this is a very theoretical way, that is a very purist way that actually can create less problems of that clash.
Absolutely.
Would that be right? Okay, good.
Absolutely. Yeah, that's really, I mean, even any database developer would love the normalization at the beginning if they can get the form.
I think it can be other way as well. Like maybe the business is not doing that sort of right thing in terms of the creating those documentation and stuff. And when the person outsider comes in and he bring the whole knowledge, what other businesses, why they are successful is because they are using other alternative ways which are much far better.
Then the ERD approach is there, right?
Yeah, I mean it can be like both ways as well, isn't it?
Depending on the situation, right? That I think Anna said, right? So if the form is there, I mean, suppose the form is there and they want, okay, I want something like that, right? Then probably normalization is the good way. But there is a trade-off always, what I can argue, right? What I can bring forward to the table, and what the client loves, right? Depending on that, we can proceed. Anyway, so this
maybe
one
the form gets improved with Sandeep's knowledge when he's implemented the database.
Yeah,
and the data gets correctly gathered in the first instance going forward.
Yeah.
But over to you, Doctor. Sorry.
Yeah, okay. No, that's a really good discussion. I mean, that's really good. Now, here, this is just one form. We're doing this is the unnormalized form, in which we know that we just put everything, the repeating group, in an extra pair of brackets, and then we try to make two tables out of it, because the repeating group, we need to make a separate table. And the statement, the fact that is given here is that the primary key of the main table should also come here, right? And create a new relation as well, because that primary key is coming here as a foreign key by which those tables become related, right? And that gives the idea of one-to-many relationship, right? Kind of thing. So, and it is in fact kind of, we can see that a one-to-many type of thing, right? That's why we put that primary key, that we know from our principle. Now, in second normal form, the definition is that it must be first normal form, plus if there is a partial dependencies. Partial dependencies are only possible when there is a composite primary key, right? So if we find here, for example, there is no kind of composite key, then we can't do anything, right, further. So the first normal form then automatically becomes the second normal form, right? So, but we see that there is a possibility of this particular table, that product ID, like the quantity, sorry, the description and the unit price, depending on that. So we need to make a separate table out of it, right? And that is what we did here, that the order product, order number, product number, and quantity. And it looks like we knew that, right? That kind of thing. The third table, if we think of ERD, kind of that, right? So it is going to that direction basically, but we are getting the table right quickly. And the product table is focusing on the real event. So we dissected that table and make two tables and try to relate them, right? So this one at this stage is 2NF because there are no non-key attributes that are dependent on partial. So there is no partial dependency. So if there is one key, then we don't need to think anything. There is no possibility of partial dependencies, right? There's only one non-key, so there's no point of identifying. So that's already separated. So
that
quantity.
product is 1NF as well.
Yes.
Because
correct. Right. So this is recording the quantity, right, of each order pair. So this quantity really depending on both, right, and they are depending on the product ID. So this is a 2NF. Now, in case of 2NF, if we try to find the anomalies, we can think of that a new customer can be inserted, so it still is there. So this is, I mean, every step we can try to think of, right? That these three anomalies can happen or not. I just skip that here. Now, in case of third normal form, so there was one, I think, key was here. If you look at the, so one interesting thing happened here, that when we did the first normal form, then we had the order product. So since there is a composite key, so that's why we only look this portion for the second normal form. And we completely skipped that because there is no way we can do any partial dependence because there was only one primary key. But in third normal form, what happens is that we have to analyze this entity to look for any transitive kind of dependency. So what does it really mean? That in this particular entity, if any non-keys are dependent on each other, and if we look at here, we can easily see that the customer number, names, address, all are really related. And this is nothing to do with the, it's nothing to do with the order number. So we need to do something here, right? So what is the thing? So that, which means that there is something we need to do, and that's called transitive dependency. So in case of transitive dependencies, what we do is we again make a new relation. So a new relation must be created for the non-key attributes that are dependent to another non-key attribute. So like the customer number, right? And so we make the customer separator up to the postcode. So if we look at here, or maybe I can do one thing here. Oh, it's a screenshot. So here, customer number, name, address, and city, state, postcode, right? So that thing can go to the customer table, and the remaining two that can stay. So customer number and all this thing, and the order becomes order ID, customer ID, and order date. And now the customer number, we definitely need to put it, right, to relate them, and these become the foreign key, right? However, the other two, like that was identified from other two relations that were identified in 2NF. These are already in 3NF because there is no transitive dependency. There's only one non-key, so there's no point of identifying that, and these are not really dependent, right? So these are automatically 3NF. So what are the final outputs? Final solution is this: order number, customer, order product, and the product. So whatever we got, right? So
if you look at these final outcome, and if I go back to my original question and think about that ERP situation, then we've got customer orders an order on date whatever, and order is built of products. So and the quantity of products and the product. So the three entities are defined: customer, order, and product. You would have found them by going through that ERP, and you would have come up with these exact three tables. So I reckon the ERP way is a million times better than this huff and puff about all the 1NF, 2NF, 5NF, 4NF, all this garbage.
No, that's
if you told me that you wanted a system that created a customer order, then through the ERP process, it was so logical. We would have built exactly these three tables in a matter of seconds, as opposed to 3 hours that's going to take us to figure it out. So anyway, that's just my 2 cents.
No, really. I mean, no, that's really good point. I mean, that's that's really useful in the class setting, that I can learn things. But what I used to do, even, I mean, this type of thing, that argument is really common in the database industry, right? Really common in the big meeting. Now, the point is that this normalization gave, it is a kind of, you can imagine, the whole process can be defined using a software, right? Because we see that it's a clear-cut steps, right? And what you're
algorithm,
saying,
just like the ERP is almost like an
that
algorithm,
I'm saying,
right?
that I'm saying. Yeah. So
different direction.
So even there are tools to do that. There are tools to do that normalization steps, right? To derive that, and you can also think. You can also think and can come up with same kind of thing, right? So that is also another way to tackle the thing. But what you said is really good, right? I mean, if you can, that's why. I mean, if you can, do the same thing, that's fine. That's okay. Yeah. Any comment? Any other? Yep.
Yeah, I wanted to say about that. The ERD doesn't cover all the aspects of normalization. So think about in an ERD, we can have multi-value attribute, which we need to break down into a separate table if we are normalizing. So ERD is just the starting point, and it's kind of, they go hand in hand. As a start, we can have an ERD and then create tables out of that and then normalize that. So it's a, I would say, two-step or multiple step process where we eventually reach to an optimal database design. It's not just having
It's just
ERD or just having normalized.
no. It's good point.
You sound like a database administrator.
No, I'm not, mate. But I have.
I've got zero experience in databases. That's why I'm coming up with. But you sound like you're coming from a point of.
I have IT background, but I'm not a database administrator.
But
yeah,
Andrew, you gave some very good insights. Andrew, since even if you're not expert, but
not even,
but your opinions are really good.
Not even a trainee, absolute novice. I've never seen a database. I've never used one before. This is my first.
No, that's fine. But the analytical things are the important ones. I mean, but yeah, that's the Mukesh said. I mean, that's really good multi-attribute. But even you can think of in the multi-attribute, all these steps are there, right? So, I mean, I'm just thinking like because the tools are there to do that automation, right? So if a tool is there to do all sort of automation, then think of kind of AI tool, for example, right? For example, they can distribute all the things, right? They can think in this way. So if an algorithm is designed, then both has all the steps. We know that, right? In both ways. But of course, there are some trade-offs in different contexts and so on. Okay. Any other comment? So really, we have to finish another example, right? Then actually it would be easier. So okay, this example is really important. Now, I just make it bigger. So this is called BCNF, a specific instance of 3NF. So what happened, this example is taken from this book. So you can download that book and look at that particular example. I actually looked at that example because this example first I didn't understand, but when I read the book, it is a specific situation that is not really realistic. I mean, that is not realistic. For example, what it says that every customer, so I just read it from here. So the table enforces the rule that each branch will serve a customer through only one salesperson. right? Now, even that line is not realistic, but we assume that this is a situation. Suppose this is the rule for this particular bank. Now, this rule is designed to explain the BCNF concept, which means that this concept is not really frequent. Most of the cases will not come up with that situation, right? Just we can quickly go through that. And there is one salesperson for so if we try to think, this information is really good enough, and if each salesperson works on only one branch only, right? So if we look at these kind of ternary relationship, then definitely one salesperson is working M to M, customer to branch. And we know from our, I think it's step 6, right, of ERD transformation, that from the multiple keys from the M side, the primary key will come, right? So this customer ID, this branch will come only this two way, right? Not the one side. So they will come work as a primary key here, customer ID and the branch ID. So this is what actually is mentioned here, salesperson, visiting frequency. So if I make it primary key, then other salesperson can be with me, but the rule saying that only one salesperson for each customer in a particular branch. So if we do that, what can happen is that so this is the situation, right? Customer nong and branch nong together as a primary key, but we can see a situation. For example, a particular salesperson for a particular branch, right? For this customer, he's working, right? And he's definitely working with other customers. But if you try to look at the salesperson, he's always in the same branch, right? So if it happens, which means that there is a dependency between the salesperson and branch owner. So if we now look at the primary key concept, is that these non-key, right? There is a dependency, right? So this is an interesting thing, that there's a dependency of a primary key on a non-key, right? So that is violating the concept at the beginning. So in that particular case, what we can do, definitely it cannot be the primary key anymore. We have to make it something like a primary key. So what we can do, we can come up with a solution like customer number, customer nong and salesperson together as a primary key. And the salesperson, we can make a separate table in which we can relate it to the branch number, right? Branch nong. So this is the kind of separation. So I'll come back again here, but if we try to relate the rule that, for example, A, B, and C, and C may determine the B, right? So B is depending on the C. In that case, I'll make A and C as a primary key, and keep other C and B as a second relation. So we dissect this table into two, in which A and the dependency, so C must be the primary key here, and this primary key, since their dependency B and C is here, we make a separate table out of it. So that's called BCNF, and we stop up to that level, and then we can basically finish all the steps up to that particular point. And if we do so, like for this customer table, then the relation becomes something like that, right? Which makes sense, salesperson, customer, and that particular one to many, the branch and salesperson relationship, and customer salesperson is many to many, and this is how we can just do the steps. Of course, I mean, the debate between ERD and normalization, but ultimately we can try to cross check what's really happening here. So there are other examples given, but I quickly want to go through the exercise, and also I need to finish the relational thing as well. So I start from here, right? Now, to do that, I just probably just quickly put it here. So just give me a time. Normalization exercise, okay. Yeah. I want to keep side by side just to explain quickly. Okay. Now, we get some examples here. The first example, probably the quality car imports. Now, this is a form, right? This is a form in which every customer has a vehicle registration number and all the service dates, and date purchase is also mentioned. Now, one thing is that a customer can have multiple cars. So then there would be another form. All right. So which means that these two definitely would be the primary key and the service date. So service date, and these are the repeating groups. So if we look at first the unnormalized table, we get something like this. Something like this. That the customer number, customer name, address, town, postcode, vehicle registration number, engine number, date purchased, comma, and then extra pair of bracket for the repeating groups, which is the service date until service cost, right?
Why aren't the vehicle information a repetitive group? You said you can have more than one vehicle per customer.
We can have, right? Can we have?
So wouldn't that be repetitive as well?
Which one?
It's got its own number, though.
This one.
Yeah, the vehicle
So the
information.
Toyota registration is different to the truck registration. Or
Makes
the
sense,
bike
or
registration.
I think it
But
depends on
not-
the date purchased. So each customer can have a vehicle on a particular date purchased.
I
Well,
could
you
have
can
placed
purchase it.
both on the same day when I won the lottery, though.
Yeah.
So then it's vehicle
that
registration.
group of items, vehicle registration, engine description, color, and date purchased,
Yep.
aren't they a repetitive group as well, because they can be multiple
not
of those?
I know what you're saying, not in this form.
Oh, not in that form. Because that form only lists it specifically for one customer with one vehicle. Yeah,
Correct.
okay, that makes sense. Yeah, fair
But
enough.
what you're saying, that second example, that we can have multiple forms, then we approach in different ways. So every
I understand now. That's right. Yeah, because the table below has multiple service dates and information, but only related to that one vehicle, one customer. That's I get it now. Yep.
Okay. So that was actually discussed at the beginning, right? I mean, the repeating groups, we just tackle that situation. Sorry, probably I didn't make it clear that time, but now that's good. Now, here we see that this repeating group, I just put it. Now, in first normal form, two steps, right? One, we need to remove that repeating groups. Definitely, we need a separate table. And the primary key, right? These two, the unique key we need to put. So we make it customer vehicle, in which we put everything, right? All the fields here, and the service. So in the service, we put interestingly, I mean, the customer number. So here the customer number and vehicle registration is the primary key, combined primary key, and it makes sense because if we make the combined primary key, only then the customer can have multiple vehicles, right? And for the service, we definitely need these two, right? This composite key plus service date. Otherwise, how can I isolate them, right? How can I separate them? So this three is the composite primary key. Okay.
What about if you have a second service on the same date? Shouldn't it be a service ID or something?
Okay. I think similar discussion we did. Yeah, I mean, my answer is always time stamped, right? Okay, it's a good point, but
what did you say about time? Sorry, because I was wondering if that's a special thing to look out for when you do an analysis. Is to
no timestamp
date being like an ID.
Yeah, it will be unlikely that the two services will be done at the exact same date and
correct.
time.
And you said
date and time.
Going back to the winning the lottery example, if somebody won the lottery, bought themselves two Porsches,
but you wouldn't be able to do the services at exactly the same microsecond.
We're a bit different mechanics probably then, wouldn't it? So then your mechanic ID would kind of.
There'll be the same date, but the date is got the timestamp down to the milli.
That's one way, and another idea is that even the description work can be kind of fixed to uniquely identify them. Make sense?
So hopefully you're not doing two oil changes on the same car.
Like oil change.
It could be that they're adjusting the same thing twice because they botched it up. But so the timestamp is the good idea, I think. Yeah, that's right.
Yeah. I mean, the coordinator, I mean, I saw that's it's better to look at the other video as well. He talked about this one, as a primary composite key, but timestamp is that I like. That's fine. So
someone just raised the question: why have the customer in the
okay, sorry,
service? I think that's
I
a good
didn't check the
question
chat.
because
I really
Yeah.
failed to
To
look at
relate back to the other table. Otherwise, what customers getting the service done?
Sorry, could it be the logbook? Why do you need customer number in service? Well, I mean,
because
we need that,
vehicle
right?
and date could get you there.
We need that, right? I mean, first of all, we need to relate these two tables, right?
Why can't you just relate it with vehicle registration?
And date.
No, we need the customer number as well, right? Which customer has that, right?
No, but vehicle and date.
yeah, because the customer could have sold his car and it's a different registration for another customer the next time.
Yeah, that's also another point. Yep. With the date purchased, like
yeah,
we can assume.
The same car. I mean, the same car can be owned by two different customers at different times. Yeah.
Yep. Okay. So yeah, that's one thing, and
but then time is still going to be the distinguisher there with vehicle.
Yeah, but you still want to relate it back for simplicity to the right owner at the right time. I guess. No, anyway, yeah, it makes sense.
Okay.
Maybe we're violating PK FK rules.
Well, especially if we're novices.
The book says let's add both. Okay, moving right along. Yep.
It doesn't make sense to me, but I'll play along.
I think it will help the customer database that when the service is done, when the customer is coming in, how much he is getting serviced in. So in that term, I think we can have the customer number, so we can analyze what customer is spending, where they are spending, and all that stuff.
No, but that's the question. I mean, in terms of optimal key, only that vehicle registration number is good enough or not, right?
Yeah, exactly. But you can just join them. You can just join them on vehicle registration. So I don't understand why you'd bother with customer number, because you just look it up the other way.
Because you can't just simply join them if the same vehicle is owned by two different customers.
But you'd purge that.
But the date would tell you if it was A or B.
But then you'd have to go into some.
Okay, I just they become foreign key at the same time. Yeah, there's the point. I think in the comment, this is like ultimately, what will happen here is that because of separate concept here, the customer and vehicle is a two different concept, and we'll see that functional dependencies will work here in the 2NF, and then they will be ultimately separated. Make sense? So that will be ultimately separated.
We'll stay tuned for the process unfolding.
Correct. Yeah. So then actually we'll come to that exact thing that we are looking for, and then if we don't come up with that, then we can discuss, right? I think we just follow these steps. Let's see. So here, but it's really a good point that only that can be done, right? Even I'm pretty sure that if you can do only this thing, ultimately that will be separated out, but we need to relate them then, right? Like the vehicle with the customer, we need to somehow relate that. Okay, we'll come to that point. So now, if we look at here, that so this is a first normal form. So definitely for the customer vehicle, I mean, there is a composite key. We need to find the functional dependency. So you can see clearly the customer, these informations are related here, and vehicle is related to the vehicle registration number. So customer, we make it separate, and vehicle, we make them kind of separate, right? And customer vehicle, you see, customer and vehicle together as a composite key and purchased. So who can tell me what type of relation it is? 1 to M or M to M or what?
It's many to many, isn't it?
Many to many, correct. Right? So that's really is happening, right? Ultimately. Okay. And now, so I think that's it. Now, here, we can't do anything basically for the service, right? For the service, it's really depending on everything here. Now, in case of 3NF, we see that, I mean, so what I'm trying to say is that for the second normal form here, we need to look at any of that attribute, non-key attribute, or depending on the part of the primary key or not. But we don't find anything, so we can say that this is straight away second normal form. And for the third normal form, we only have to look at the dependency between the non-keys. So we can see this table. So this table is already here. So customer, I mean, there's no possible dependence here, not here, not here. So this is only one attribute. So we don't need to simply ignore it. Now here we see that mechanic ID and mechanic ID, what's that? Sorry, I think here mechanic mechanic ID and mechanic name in the first normal form. There's a service table. They have the dependency, right? So we can only keep the mechanic number here, and we can make it a separate table. That we really did here. That mechanic ID, and mechanic name, and the service table has only the mechanic number as a foreign key, right? So now that's basically 3NF or BCNF, right? Up to that point, we analyze. Now look at the second exercise. I'm just running out of time. So, but this is really important example. I'll probably go through quickly on this exercise. Now, this is the first time we can see three view of a single database, right? Three view, and we'll see the steps, what needs to be, what we'll be doing. So subject report, by looking at the course kind of thing. So we can see that in the subject report, another is student report, lecturer report. There are three reports. So in the subject report, we can find that subject code, subject name, subject description, subject credit, right? So only these four. So we can just put it, and the subject ID is the primary key by looking at the data. And if we try to see second NF, there's no repeating group. The primary key is defined, so it is first normal form. For second normal, there's no partial dependence because it's only one single key, so it's second normal form. For third normal form, there is no kind of, transitive thing. So there's no possible dependence here, so it is third normal form. So done, right? Nothing can be done here. Now look at the second report, which is the lecture report, right? In the lecture report,
can I ask? That's just because of the specifics within that report.
Absolutely,
if you go back one slide, because for example, can you have a situation where the same subject code, subject name appears, but oh no, in this case you probably can't. No, yeah, all right.
Okay, so we'll see that. I mean, definitely you can think of. Now, this is a four kind of thing. Now, next is the lecture report. So in the lecture report, what happens is that lecture details all these, and this is a repeating group of the subject, right? Subject code. So this lecturer is lecturing these two subjects, right? So what I do is I just do the repetition here. Sorry, I just do the repetition here, and we can see that the lecturer number and this is repeating with extra pair of brackets. Now in first normal form, I definitely need to make it separate. But if I make that a separate relation of teach, for example, then definitely I need to put the lecturer ID here, right? Then I can't relate them, right? And the subject number, definitely the partial key. So they are the composite key. In 2NF will only deal with if there is a possibility of partial dependency, right? So if you just see it, straight away we can see that there's a dependency, right? Because subject ID and subject name, they're dependent, right? That doesn't depend on which lecture is teaching that, right? So we make a subject table and teach table, which the lecturer ID and subject number, right? And so on. So we can think of one to many or one or many to many kind of thing, whatever is suitable. Now, lecturer is same. So if there is only one primary key, so there is no point of second normal form investigation. For the third normal form, we only look at the non-key relationships, right? Non-key kind of thing. And I think that's it. Nothing can be done. I mean, there is no kind of transitive dependency. So straight away, it will go to the third normal form. So this is the outcome of all the tables in the third normal that we really got, right? Now, so far we got one, result in one view. Another view gave another set of results, but we see the lecturer is common in both. Sorry, subject is common. Okay, so that is an interesting thing that we'll see after finishing the next one. So the last one is the student report. So in student report, we put all the things with the subject code, subject name. This is the extra pair repeating groups. So we need to remove that. So to remove that, we put academic record with the student ID as a primary key to relate that to that subject, right? Which subject the student to. Plus year semester as a kind of, primary key, because in different year, right? That we need to define. Now, in second normal form, we only look for the partial dependencies. So, I mean, this is just only one primary key, so you can't do anything. It is already second normal form. And academic record, we can see here that the subject name and subject ID, a clear dependency here. So we make subject table, and the academic record has student and subject ID, primary key, year, semester, all these three are primary key, and grade, right? Good. So subject here, and this is the foreign key because student has the student number, primary key, and subject has the subject number, primary key. So they appear here as a composite key, but both are foreign key because they're coming from the another table. Now in 3NF, we can definitely only look at this first table because there is only single non-key, so we don't need to investigate anything. So here we can see that what we can see that the lecturer ID. So definitely it is a completely separate, different thing, right? Nothing to do with the student. So lecturer ID and lecturer name, we can make a separate table of lecturer ID and lecturer name. Lecturer ID is a primary key. And student table has now only the lecturer as a foreign key, like to relate them. Right. So this is the final outcome. So if we summarize everything here, so we can see that from the first form, we get this result. From the second form, we get this 3 relation, and from the third one, we get this 3. Okay, so what are the steps? The steps are that when we can find 1, 3, and 7, so 1, 3, and 7, they are subject. So from the subject, the rule is that we need to take, it makes sense that the largest number of attributes. We need to take the relation which has the largest number of attributes because that is covering the complete scenario. If we take the smaller version, that is not covering everything, right? That is the reason. So from 1, 3, and 7, we pick this one, or like the 1. And from 2 and 6, so if we look at the 2 and 6, same table, 2, lecturer, and 6, we take the bigger one, like lecturer ID, name, lead office, and the other unique tables we just put as it is, right? So this is the final kind of, the entities is a combined result. So I just give a 3 minutes break, then I'll start the relational algebra, right? Because there's a lot to discuss. So probably a quick question do you want, but otherwise I can just take the break.
Can you extend
5
it to
minutes?
5 minutes?
5. Yes,
Let's make
sure.
it 5 minutes.
Yeah, no, definitely 5
All right,
at least.
thanks.
Okay, no worries. See you then. Okay, so welcome back to week 3 lecture. Now, relational algebra is the next chapter, and this is the starting point of query. So we'll start looking at the query from algebraic point of view using different notations. And some of the functionality probably you're aware of before, but we'll see. Now, in lecture 2, we saw data structure like 3 major aspects of relational data model, like data structure consists of n RE two-dimensional tuples, tables, relations, right, whose domains, attributes are atomic types, like one single value. Data integrity, we talked about referential integrity is one of the main important thing. Entity integrity, like each has unique kind of values. And data manipulation, set of algebraic operations for data manipulations. Now, we'll see it here. I'm just quickly going through. So, few tables are there. Student is one table. Takes, subject, course, enroll, right? So, where are we? So, it is basically we normalized all the tables. Either we got the normalized tables, or from the ERD, we made all the tables, right? Everything is there. And then we need to do some operations to do the queries, right? That is we're learning here. But we need to know that to do a query, how those multiple tables are becoming related. So if we want to do a query on a single table, that's easy. And then we'll see the complex situations where multiple tables are there. For example, if I want to see which students live in Bandura, so we definitely need to know that the tuples from the student, right? So Bandura, so definitely which students. So look at the student table, and then suburb should be the Bandura. So only this particular portion, right? That really we want to see. Now, which students are doing course 113? So first, for example, now this is an interesting thing from 113. So course 113, which means from course, so 113 is there. So which student? So from student table, we can see only the ID, right? However, from here, from enroll table, we can find out the SID. So we can see that these table is involved, right? So this table, first we need to identify that tuple, and then we need to compare that tuple to here, right? This table to know the name of that particular person. Like 1108 is here, Robert is the name, right? So we can see that we first dissect this tuple, and sometimes we need to dissect a column. Sometimes we dissect a row. Sometimes we can need to look at the column. So these are the requirements. So that's why some of the operations we need to identify. From a relation, choose those tuples that have a certain property. Choose some attributes from a set of tuples and match one set of tuples to another. Right? These are the basic steps. Now, some discussions again. A note is that the video are well descriptive. Some of the video tutorials are there. There are many informations are there, but I'll just try to skip. But more informations are in the previous videos. That was done during the COVID time, so it's really many discussions are done there. Now, in case of relational algebra, a suite of operations on relations, and one point here is that we do some operation. So when we do the operation, then there must be operand, right? And on operator. So we'll see operator and operands. So operands are here basically the relations between two tables. We can do an operation, right? And the result can be another set. So we'll see the set notation. We know one of the idea of the set is that we can't really put duplicate thing, right? We can't really put duplicate thing. So the same no repetition situation will really happen in the outcome. So create a relation by choosing from student and tuples where the suburb is Bandura. So it's an operation that takes one operation and produces another. Relational algebra is the basis of the implementation of most current database system. There are 8 operations. We'll try to see all these operations pretty much quickly. I think this is not difficult. I mean, we'll just go through that and we'll try to explain as much as possible. So the first operation on a relation is called projection. So P. So since it's P, which means it stands for the pi. I mean, this is how we can know that projection is pi. So what happens is that find the names of all the students. So when I talk about the student, it is the tuple, sorry, it is the relation table, and names is the attribute, right? So what I do here is that pi and put the attribute name, and this is the relation, which is the student. So when I do it, then it will, what it does is extract, I mean, just show that name a column. So pi is the symbol for that. And for example, if we do something like that, so this is only one attribute, but if we show attribute list like C2 and C5, if we put a comma of R, then we can get something like that, right? Only the column will be shown, right? This is the output. Now, for example, if we look at this example of projection, that subject, noun, name, and department is given. So if I do pi name department subject, it produces the output of just name and department, right? These two. And pi name subject, it only produces. Now this is an interesting thing, is that pi name subject. So from the subject, if I put the name, so you can see that algebra is repeated. So, but only one time it is appearing, right? Because no repetition is allowed. However, when we showed name and department both, then if the complete tuple is unique, we can only delete that. Otherwise, we can't. Since algebra is there, but these are different, so we can't really delete anything, right? We have to put everything. So this is an important thing to note, right? So this is the projection. So projection is actually identifying the column, right? Selection. So selection is looking at rows or tuples. So selection S, so sigma, is used for selection. So where the project operator takes a vertical subset columns of a relation, the selection takes a horizontal subset rows, right? So choose from R each tuple where the condition holds. For example, if I put something like that, select some condition of R, so it will probably extract R2 and R3, I mean, depending on the condition, right? So it just picked the kind of horizontal subset, which is the tuples, selected tuples. An example, subject table is given and the query sigma department equal to CSCE subject. So pick only those tuples who have department CSC. So pick these 3. So pick these 3, the first 3, right? First 3 I just selected. So that's the selection. Which students live in Bandura, right? So this is the table given. So this is a complex. So when we see a complex like that, complex expression like that, it can be very big. We start from the main one, which is the inside one. So first select suburb equal to Bandura students. So from the student, you just select the people. So the select is all the tuples. So these two. So this first and second row. So in other words, the first, what will happen here is that first it will pick these thing, right? Sorry. So it will pick these portion first, and from this table is actually this portion, right? And then when you do the pi, it just pick these two, right, of this. So this is actually what happened here. So first we'll finish that portion and then we go here. Okay. So that's why Glenn and Norman. So now the question is, let's see who can answer. If I change the order of the operation, what will happen? Like if I put pi name inside and sigma suburb bandura outside, who can tell me? Anyone?
You'd be looking at rows and columns differently.
Yeah,
well,
so different.
You'd only pick the name column, but then there'd be no
Nothing.
no bandura.
Yeah, so it's just empty, right? Nothing will be printed. So
just one thing that I picked on what you said. You said
Yes.
that the suburb, the sigma, it will return rows 1 and 2. Sorry, you said rows 1 and 2.
You mean 2 and 3?
2 and 3. 2 and 3.
Meant the bandura to return
Okay.
2 rows with bandura in it.
No, I wanted to make sure that I wasn't starting from row 0 or something.
B.
Oh, I see. Yeah, I mean,
row B2 and.
Well, I mean, index is not related here, right? I mean, we don't just whatever.
No, but it's what you said. You said rows 1 and 2, but it's actually.
Oh, I see. So, okay. No, that's okay. Oh, that's okay. Okay, so that's this is the thing. Now, next one.
I have a question. I don't know if it's relevant. But I think where it showed all of the tables, there was ID and then student ID, so SID. And I just wondered from the start whether you could all call them.
Oh,
SID,
I see.
Even sometimes later on are going to go ID to
okay, but in the same picture, probably that was fine. That was fine.
I think it was slide 4, the introduction.
Oh, okay, there. Anyway, do you want me to look at?
Yeah, slide 4, that one. 4.
Yeah.
See, the student table just has ID, but then in takes it's been
converted. Oh, then it's a different
ID.
Yeah.
But that's why in the student table it's just not already SID.
But the table, the column names can change even
can
though
change.
Have the same information.
Just for a demonstration purpose, in every slide.
Okay, there's no rules.
No.
Okay,
Yeah. Just is explained here.
Done.
Now we come here. So this is the steps given, steps shown that select the suburb bandura, that we just explained. And finally on this table, so this table is basically for example, once we do the internal operation, then we get a temporary table. So the next operation will work on the temporary table, right? That we already discussed. So this is how we can generate the final outcome. Now the next one is, I just put some notes, is the union. So in case of union, is that two relations, right? There are two relations. So the union of the two relations is formed by combining the tuples from one relation with those of the second relation to produce a third one, right? And now one question is that R1 and R2 have to be union compatible relation, which means that have the same set of attributes. So there are two definitions. I just put it here, that they must have the same number of attributes or columns. And second, every column type, like the data type, should be exactly the same, unless you really can't do the union operation, right? So two things. One is the same number of attributes. Second, their data types should be same, the corresponding data type. Like the first table's first attribute and the second table's first attribute should be the same type. Then we can find the union operation. So in case of union operation, we just, combine them. For example, subject code and subject code, there are two relations. So when we combine them, we only take, whatever is, if there's duplicate, we just take one for the duplicate thing, because we know the inset operation, we just take only one kind of thing, right? Similar things. So now in case of union, for example, if two relations, I'm just trying to think. Okay, so this is an example that if two relations have the same set of attributes, they can be added together. Example, what are the SIDs of students doing the subject 21 or subject 29, right? So what we did is that select 21 SID 21 from the text table, and then picked only the SID, projected only the SID. We get something like that. and do exactly the same for 29 from the text table. We get something like that, and then we do the union to get the output. So this is exactly this expression. It's a big expression, but in the union, so if you can see here, union, so we think it as a first relation and second relation. In the first relation, we do the internal thing first, and on the temporary table, we do the outside thing. Similarly here, for the second relation, we do the internal thing first. On the temporary table, we do the, and that is exactly is executed here. Now, just a quick note, I just put some additional note here. You can think of later on, I mean, that's fine, that using OR operation, we can exactly do the same thing, basically. For example, that pi, I just put text pi SID, I just picked the SID finally, but if I take the sigma S nong 21 or S nong 29 from the same table, so you pick all these and then you just project it, right? So this is essentially the same. They are producing the same kind of outcome, right? All good, everyone, up to that point? Okay.
Yep.
The intersection is just the common thing, right? So the whatever is intersections, is a set operation type of thing. So in the intersection of two relations is a third relation containing the common tuples. Both R1 and R2 must be union compatible. Again, the definition of union compatible is that same number of attributes and same data types, right? These two definitions. It is not explicitly mentioned here, but that's the definition. Now, if we do the intersection, we only get the common portion, right? For example, the dB, 21 dB is in both tables, and 30 is in the PRG in the both tables. So that is the outcome of intersection. Now, exactly similar example is given. So just try to imagine that this is the AND operation, right? AND operation. So an AND operation by logic is kind of, intersection. So the similar example that we discussed before. So select, 21 and do the project, and select 23, do the project and do the intersection. Or the same thing you can do using the AND operation, right? That we discussed alternatively. So same output it can really produce, right? Intersection. So, and
So,
now
so
the,
was it really accurate what you had in the last? If you go back a few slides where you put the alternatively, this one here, you said alternatively,
Yep.
it's equal to that or that.
Yeah.
But that or that implies that it also has the intersecting parts as well.
No, only because no, it's atomic value. So either 21 or 29 it will be picked up, right? So what I'm saying is a 21 or 29. So if you look at the table, like either it will be picked up this 21 and 29. That's it.
Okay. Yeah.
Right. Yeah. Okay. So and right. So this is the thing. And or these two are really, really common. The difference, there's not that much use, but the difference is that the difference of two relations is a third relation containing the tuples, which occur in the first relation, but not in the second, right? So not in the second. So R1 minus R2. So if you look at the difference that this minus this, the minus sign is basically to whatever is here, you need to deduct from there. So 21 dB is probably not here, and 21 SGT is not here. 30 PRG is there, so I can't take that. So pick everything, put it here, right? Okay, so some comment came, union, and yeah, correct. Union or intersection. Yeah, just selecting. Just trying to line up the theory. Yeah, good. Yeah, good comment. That's fine. That's fine. Yep. So these are the basic set operations. Really, yeah, that's good. And really fun. These are just the operation. Now, next one is this is one of the idea that reveals that when we do the in the SQL we need that, because it actually implies that the number of operations will grow if the table size is big and if we do more Cartesian product. And in SQL query, when you join the tables, we need to deal with that particular situation, right? Okay, so if we look at here, that what is product? So the product or Cartesian product is in two relations. We need to make a third table in which all combinations, every tuple, against each tuple, we need to put it here. So for example, A, we need to put X and Y together. So AX, AY. B, BX and BY, right? So C, CX and CY, D, DX and DY. So total 4 times 2, 8 tuples. So it is joined. So the relations on which a product operation is applied do not have to be union compatible. It's not, because we know that union compatible is same number, but we don't need that. We just combine. So we never do the Cartesian. Doesn't make sense, because if you do that database, it doesn't make really sense, right? I mean, we'll see an example why. I mean, just try to imagine that this is a student ID, and this is ID and name. So this is another portion, ID and address. So this ID will appear twice, right? And so on. But we need to deal with that situation, and if we try to define that, like ID1 with one of the entries ID1, so that makes sense if we do the pair up, right? This is the exact relationship. But if I try to pair up with ID1, student ID1 with student ID2 and put it there, that doesn't make sense, that relation. But Cartesian product is doing all sort of combinations, and then which means then we need to select somehow based on the equal kind of value that we'll very soon see. Now in SQL, we'll come up with an idea called join. So join is the popular term, is the term in SQL, in which we get the subset of the Cartesian product. And that makes sense, because we only take those subset where the IDs really are related, right? Same IDs, and all the informations we just combine together. That's why the subset of Cartesian product is mentioned here for the join, and that we'll be using in the SQL from the next week. Now look at an example. Takes has 2 entries and student has 4 entries. So if we make a Cartesian product, we get 2 times 4, 8, right? And now if you can see that this 1108, 1108, it makes sense, because which means that this ID took this course and he's the name, right? It is the name. But this table, if you see that 1108 and with 3936 ID, this row doesn't make any sense, right? So which means that Cartesian product can do lot of things, but we need the join in which we need a subset, which makes sense. Yeah, okay. I think one comment came. Yeah, correct. I mean, we remove the duplicate tuples. We remove the duplicate ones, right? Remove the result output. No, depending on what do you mean by duplicate? So all the
No,
attributes.
it was my comment,
Okay, because
and I was saying
yeah,
I didn't think union was an OR operation. I thought union was an AND operation.
Yep. Okay.
Because you said to the previous comment that union is an OR operation, and that wasn't my understanding.
Okay. So is it okay now?
No, because is union an or an AND operation?
Union is...
Nicole's got a hand up. I don't know how to do that function. Sorry, people, for jumping in.
Intersection is AND, right? And union is OR. Right? Union
Why is union or? I thought you combine table 1 and table 2 and show me table 3, but don't take the...
or means like take everything from both table, and the common portion just...
Oh, you're saying
once.
all A double L.
No, OR.
Oh.
Sorry, I wrote it here, right? Can you see that OR? Anyway, I mean, that's right.
The union is not in that formula.
Is in the formula. So what
no,
I'm saying is...
No, but in your alternative one, it's not. In the union one, you combine in...
Yeah, I put OR, right? Can you see? So what I'm saying
is... that's no longer a union formula though, right?
No. What I'm saying is that the union is doing exactly whatever output it is giving, this OR is giving exactly the same output.
Okay, but when you do the union formula without your alternative, you were
then OR is not.
you were doing an add combining two tables to
combining means
two rows to get the result.
Yeah, combining means you take everything and the common portion you take just once.
Yeah. Okay. But it's an add, not an OR then.
What do you mean by that? Okay, we'll go that after we finish it if you get time, right?
All right.
Okay,
so I think it's just me not understanding the distinction between your two formulas, but I don't think it's a problem. So thank you.
Okay, all right. Now join, in case of join, now this is an interesting one because Cartesian product, we know that it is just irrelevant. Now in join, it will do the combination and when they are, based on a condition, we'll try to join it. So for example, if the way it is joined by this symbol R1 with some condition and R2, and we get a result. So when they match, for example, ARX and BRX, right? Because they match. So we'll see some condition, then we can come to that point. So for example, if we see here, that takes student, it's like if you do the Cartesian product, it will produce everything, right? We know that 4 times 8, all these things. But if we take takes and join operation, SID equal to ID. So, in all these combinations, when SID equal to ID, that makes sense, student. So the output would be only exactly like this one. So, this portion, then whatever is equal, right? 1008. So I can't remember. So whatever was there, for example, the common portion will be picked up. That is the join kind of output. That is what we expect, similar to that, right? So which means on the previous Cartesian product, if you do the join operation on this condition of equality, then it will pick up only the meaningful thing that we'll be using in the SQL. For example, enroll and student, right? So which students are doing course 113? So first select course 13 enroll. So when we select, it will pick up what? It will pick up the tuples, right? From the enroll table. So 110 and 13 is R1, and then we do the join relation with this table of R1 with the student table, right? So R1 join SID equal to ID student. Then you'll pick that SID, course ID, which is this 2, and name, corresponding name, Robert, which is the equal one, and the Q, right? This one. And then on R2, we do the pi project. So pi name. So pick only the name. So this is the whole expression. So the internal one is this one, right? So this is the join operation. R1 is this one, and and this is the portion of second part, and then the pi at the bottom. So this R3 is producing this Robert. So this is a step-by-step thing. Yep.
Yeah. Can I ask a question? I guess
Yep.
I'm looking at that bottom statement, and it's probably consistent with what I wrote. It seems a lot more complicated than just writing a select statement, which is ultimately
going to, because this is not the practical thing, right? I mean, this is just the ideas. Good point. Yep. Okay, now the next one, then I'm finishing, is the outer join. So in case of outer join, what happens is that we match plus, but on the left table, we pick everything. We take everything by force. Now, if we take everything on the left side, and if we try to match everything on the right side, definitely we can't get everything out of it. Some of the values should be null, which makes sense, right? And that is the outcome here. So it is basically the join, but with outer join means on the left portion, we take everything, and on the right portion, the unmatched attributes, the kind of values should be null. So for example, if we do these two outer join, A, B, C, so I put A, B, C and all these values, and then try to match R, R, X, right? And then R, S, right? B, so B, R, and X, and then CV, and we try to match, nothing is there, so it is null, right? So this is basically the outer join and so on. So you just some examples are given, so I just try to skip that. Okay, I try to finish that, so probably after 10 minutes we'll be starting the lab, right? Any quick question on any of these? I think some questions came in here. The slide is missing condition X equal to R. I'm not sure. What does it mean?
Will the lab go for 2 hours tonight, will it?
Yeah.
Yeah.
What I'll be doing, just I'll do some exercise, 10 minutes kind of thinking, and then I'll do the solution and so on.
Is it
Doctor,
just one lab a week? Because I was going to join tomorrow's lab.
Yeah, definitely. Because there are other labs. There are 3 labs. So I think
Cool.
you can join in your times, right?
Yeah, I'll
Okay.
go and digest this. Thank you.
Excellent. Okay.
Doctor, can I
Thank you.
ask?
Yep. Yes, please.
Sorry,
Yep.
on slide 19,
Okay.
what's the formula for difference? I don't know if I missed it, maybe.
One by the
Okay.
other. One
Yeah,
deduction by
one,
the other.
just deduct the
Yep.
other portion from there, right?
But is there a
So
formula? Like, you know how there was the pi, the sigma. Is there an
I think
equivalent
that
formula?
R1 minus
no,
R2.
just the Venn diagram is easy to explain that, right?
Okay, so we don't need to convert it into a specific format.
Yeah, I really didn't think about that, but I'll try to think, right? If I
Okay,
can get
thank
any
you.
formula, but yeah.
Yes, thank
Isn't
you.
it the relationship algebra in the blue in the center there? R1 minus R2 is the
No, I think that's
so
just
division way.
explaining
only
the
R1. So
tables.
this
Yeah.
shaded portion will be taken only, right? Okay, I think that's it. So okay, see you all. Thank you all for staying tonight. So see you tomorrow. See you next class.
Thank
Thank you all.
you.
Thank you.
So you're switching. Yeah. Okay.
Thanks.
You're switching over, are you?